can't keep skipping AP Bio.
Thank you. Alright, so we're going to continue talking about the derivative today. We introduced it yesterday. Just a little housekeeping type thing before we get started. For those of you that are interested in enrolling through Seton Hill for college credit, the original deadline was September 28th. They have extended it to this Friday. So if you wanted to enroll but you forgot, you're still okay. All right, you have till this Friday to follow the instructions on this paper. Does anyone need an extra one by chance? No? Okay, you can sit right. All right, so based off of yesterday, what was our definition of the word derivative? When I say derivative, you think what? Good, Dan?
Slope of the tangent line.
Slope of the tangent line. Okay, we spent quite a bit of time yesterday looking at a graph and analyzing the different kinds of lines we can draw on a curve. We looked at tangent line and we looked at secant line. And through analyzing those two different types, we saw that the secant line could eventually become the tangent line if we dragged that secant point closer and closer and closer to the tangent point. Do we remember that concept yesterday? Okay, so big idea in this section. When you hear the word derivative, you think slope, and particularly the slope of the tangent line. Tangent meaning one point. Okay, one point, one spot, one location. We'll eventually get to some other types of problems where that signifies one moment in time, like at this particular instant, what's happening. Okay, we'll get there eventually. But today, we're just going to practice how do we find the derivative. Okay, mathematically speaking, how can we figure out the slope of the tangent line? And we investigated that idea yesterday. In order to calculate the slope of a tangent line, we're going to be using a limit, and not just any limit like we were looking at in the last unit. We're using this specific limit. We are letting that h value go to 0. Do you remember from yesterday what the h variable represented in our little picture or diagram we drew? Maybe you got to flip to check it out. What did the letter h mean? Can you find it? Good, Braden?
It is the distance between x and x plus h.
Okay, so it's the distance between your two secant points, okay? One of those secant points happens to be the tangent point, but we had to choose another point on the curve for us to actually calculate the slope. So h is the distance between your secant points. Thank you. Okay. So as we let that distance get smaller and smaller and smaller and smaller, aka approaching 0, we're going to analyze the slope of that secant line. Notice how we have a y value minus a different y value, and we saw yesterday how that was divided by the x value minus another x value, but didn't the x's cancel? We saw that. We were just left with the letter h down there. So in order to find the derivative, the slope of a tangent line, we are specifically and always going to use this limit. Okay? Now that limit might change depending on the equation we have. We're going to take a look at some examples of that today. But this is a very, very special limit that represents the derivative. Okay, the slope of a tangent line. So let's take a look at our first kind of example here. Let's say the f of x equation, okay, the original graph that we're kind of starting with, is 2/3 x plus 3. We're going to try to find the derivative, okay, the slope of the tangent line at any location we want. So in order to do that, we're going to use this limit to help us plug in certain things, solve the limit, and see what we get. So let's go ahead and write limit as h approaches 0. The first piece in this special limit is f of x plus h. What is that notation telling us to do? What does that represent? What does it mean? What do you think? What do you think, Braden?
Plug x plus h in for s.
We're going to take the x plus h quantity. Notice how that's inside the parentheses, so that's representing an input. Okay, we're going to take x plus h and plug it into all of the x's in your original equation. In this case, we only have one x. So if we were to take x plus h and plug it into that x, we would have 2/3 times x plus h plus 3. If we continue to look at this derivative limit setup, we have to subtract f of x. What's f of x? The original equation that you're starting with. Yep, so we're going to subtract the 2/3 x plus 3. Bless you. Make sure you put that in parentheses, because if you're subtracting f of x, you're subtracting the entire function, okay, every little piece. So that means we'd have to distribute eventually that negative through, okay? And if we continue with the way this derivative limit looks, this is all over h. So this specific limit, with the way we've set it up right now, is going to give us the slope of the tangent line at any x location we want. Let's go ahead and simplify it to see what this derivative is. So we can maybe do some distribution to get rid of parentheses. Maybe some things would cancel out in our favor. Let's see what happens. So 2/3 x plus 2/3 h plus 3 minus 2/3 x minus 3 all over h. Anything going to happen now that all the parentheses are gone? Yeah. Gone, gone. All right, so we're left with 2/3 h all over h. Let's not lose sight of the fact that we're still working with a limit, and direct substitution is typically our way to go when we're evaluating those. If h is going to 0 and we were to plug in 0 for the h's, notice how we would still have 0 over 0. So there's still a little bit more we can do. What else can happen? Divide the h's. Gone. So it looks like we're left with 2/3. Okay, we could try to substitute in the h value of 0, but there's no h left to do that. So this 2/3 in the end is representing the derivative. Do we remember yesterday our little symbol, our notation that means derivative? What it looks like, or how you say it, maybe? Yeah. F prime, okay, prime is a little apostrophe. Okay, so our derivative at any point, okay, the slope at any point on this graph is 2/3. The slope at any point. That's our definition of a derivative. We doing okay? We're going to try another one. Okay, we're going to step it up. This time, our second equation is quadratic. Notice how we have a little bit more x's in there, but we can handle that. If we're going to find the derivative, we're going to use our specific limit definition of a derivative to do so, but we're going to have to apply it to this equation, okay, this original function. So the first piece in the limit is telling us to take x plus h and plug it into all of the x's. If we continue to look at the limit, it then wants us to subtract f of x, but that's just representing the entire original equation. And that's all over h. Right, so we're going to try to get rid of the parentheses. That way we can combine some like terms. Hopefully a bunch of items cancel out. That way it's less for us to deal with. And we'll keep going from there until we get our derivative. Okay, so you got to think of your algebra. We have x plus h squared. You got to write it twice, go through a FOIL process, and then distribute in the 1/2. Are we okay if I go directly to what that would be? Are we there algebraically in our heads? We can do that? Okay, if you need to write it off to the side, by all means do it. I'd rather you write it and get it right than not write it and get it wrong. Okay, if we continue to distribute, that's easy peasy. I'm running out of room. Can we go pencil happy with our crossing out? What's going to go away? Let's see, the x squareds, the 2x's, and the 3's. So xh plus 1/2 h squared minus 2h all over h, that's what's left. If we tried to plug in 0, okay, just for the h's, we'd still have 0 over 0, so we have a little bit more to do. Where do you want to go from there? Yeah. Okay, if we pull an h out of the top, notice how that would cancel out with the h down below. So we're left with x plus 1/2 h minus 2. So now if we try that direct substitution with a limit with just the h going to 0, what are we left with? We thinking x minus 2? Okay, so we'll say f prime of x, okay, the derivative, specifically for this beginning equation, because notice how our answer for this derivative was different than the 2/3 we got before. Okay, it all depends on your original equation. The derivative in this case is x minus 2, so this is representing the slope at any point. Okay, you can choose whatever x value you want and plug it in, and that'll give you the slope at that location. Okay, the slope of the tangent line. Are we doing okay with derivatives so far? It's basically a limit, and that's why we had to do limits first. I know we probably didn't like them. Personally, I feel that way, but it was a necessary evil for us to get here. Okay? So speaking of these derivatives, again, notice how they're different. This one was 2/3, whereas this one was actually an expression, right? We still had an x left. Let's talk about this difference, okay? If we were to compare this derivative to this one, what are some similarities or maybe differences that you can identify? Maybe you can compare what the derivative looked like in comparison to the original function. Can we make some connections? Let's think about this. In the first block on the left-hand side, if you're left with 2/3, what type of function is 2/3? Linear, quadratic, cubic, absolute value? If you have just a number, what's the name of that type of function? Yeah. What was that? Not quite. I'll come back to you for the next one. If it's just a number? Constant. Okay, so the derivative for the function of 2/3 x plus 3 was a constant function. How would you classify the derivative for the second example we did? This x minus 2. Anastasia, what's that kind of? That's linear. Okay, bless you. So the bless you. The derivative for the quadratic equation was a linear function. Okay, so let's make a connection here. Let's see if we can look at something. In our first chart, okay, our first block over here, the original function was linear, okay, 2/3 x plus 3, and when we found the derivative, it changed to a constant. In the second block we did, the original function was quadratic, and notice how the derivative was linear. Can you make a connection between the function you start with and what its derivative should be? What do you think, Braden?
A degree lower.
A degree. Do you remember what a degree is? The power, the exponent, okay? Notice how the degree in a linear function is 1, okay? But the degree in a constant function is 0. You don't have an x in a constant function. If we look at the quadratic, the degree in a quadratic is 2, and the degree in a linear is 1. So there's a little pattern there for us to kind of be aware of. Okay, maybe we'll say it appears that the degree of the derivative, okay, f prime of x, is 1 less than the degree of f of x, okay, the original equation. So that's nice to kind of anticipate, because when you're going through these solving derivatives, or at least figuring what they would be, if you get something that's a degree more, okay, maybe you did something wrong. Okay, so it appears that the derivative should have 1 less degree, 1 less power than the original function does. Okay? Let's go ahead and try some more practice of these derivatives, but we're going to get into some good equations like square roots and fractions. But the process doesn't change. Okay, we're still using the same limit definition of a derivative. All right, so let's go ahead and focus on the derivatives first, and then we'll take a look at the tangent lines at the bottom of the page. Okay, so in this case, our original function we'll say is a square root. We want to figure out what is the derivative. Okay, what can we use to find the slope at any point? So we'll set up our limit. We first have to plug in x plus h for all of the x's. In this case, there's only 1, so that's nice. We then have to subtract the original equation, and that's all over h. Alright, so keeping in mind that this is a limit, we got to think about some of those techniques that we talked about in the last unit to help us simplify or solve limits. Where do you guys want to go from there? Split them up? You mean, oh, because we have a single term denominator? Okay, you could split them up, but unfortunately it's not really going to get you anywhere. Okay, because if you really think about it, if you just have this fraction, you're going to have, and then you plug in 0, you're going to have the square root of x plus 2 over 0, right? And you can't divide by 0. The same thing's going to happen over here. Okay, so you could split them up. There is a single term denominator, but that might not be our best interest here. What's another technique that we can try? If that one doesn't work out, let's try something else. Yeah.
Since it's a square root, could we use conjugates?
Let's use.
X plus 2.
Yep.
Under the square root.
Perfect.
Move that to the bottom.
Let's do that.
Equals 0.
Let's use a conjugate. Okay, that crazy word from last unit. Notice how the square roots are in the numerator. What would our conjugate look like? Remember how a conjugate works? What do you think, Braden?
You just switch the outside sign.
You switch the outside sign. So you keep the terms the same, but instead of, in this case, subtracting them, we're going to add them together. So there's our conjugate, and we have to multiply that up top and down below because we're dealing with a fraction. You got to keep it balanced. Now, since we're working with a conjugate and going through the FOIL process would be necessary, the inside and outside terms are always going to cancel. I think we discussed that characteristic because one's positive, one's negative. Okay, they're going to go away. We only really have to focus on the first terms and the last terms. So in terms, when you look at the numerator, the top pieces, we're going to have a square root of x plus h plus 2 times another square root of x plus h plus 2. The square roots would go away, so we're just left with x plus h plus 2. Multiply outsides, multiply insides, those are going to cancel each other out. So now we just have to do the lasts. If we take a square root of x plus 2 times another square root of x plus 2, the square roots are going to go away. So we're just left with x plus 2. But we have to be careful because we are also taking a negative square root times a positive square root, which means we would have to subtract that quantity that's left over from those square roots. If we multiply the denominators, we're going to have the original h that was down there times that crazy conjugate. Alright, do you notice anything that's going to happen? A lot of these limits should involve canceling out some items, if you haven't really noticed that by now. Okay, so when you're dealing with these derivatives, canceling things out should kind of be a clue that you're going in the right direction. Anything going to cancel out with what we have here? Maybe take a look at the numerator. If you were to distribute in that negative, maybe that'll make it a little bit more apparent. We would have a negative x and then a minus 2. Do we see how the x's would go away? Right? And then the 2's would go away. So essentially we're just left with an h up top. But what's going to happen with that h up top? Cancels with the h down below, right? Okay, so a lot of canceling. In the end, we're left with a 1 placeholder up top because everything went away, everything canceled out. And we just have that conjugate down below. Okay. So let's try our direct substitution now that we did all the canceling. If just the h is going towards 0, we're going to have 1 over the square root of x plus 2 plus another square root of x plus 2. Those are like terms, aren't they the same square root? So we can say we have 2 of them. Okay, there's our crazy derivative. So we'll label that f prime of x. Ryan, can you do me a favor when you get a second and shut that door? We ready for another one? We'll take a look at a fraction example. Okay, let's check out the limit as we let that h distance between the points get smaller and smaller and smaller and smaller. Our derivative always starts out with plugging in x plus h for all of the x's. We then have to subtract the original function, and that's all over h. Okay, but this is still a limit. We still got to use those techniques from the first unit. Where do you guys want to go from there? We have fractions galore. Can we start to condense some of those, perhaps? If you look at the numerator, we're subtracting fractions, so what needs to happen in order for you to subtract fractions? Common denominator. All right, so we're going to multiply the first fraction by x plus 2 on top and bottom. Okay, that opposite denominator. So that means we're going to have to multiply the second fraction by x plus h plus 2. Okay, its opposite denominator on top and bottom. Okay, so let's go ahead and do that. If we take 3 times x, we'll have 3x, and then 3 times 2 will give us 6. Let's go ahead and do the other numerator. We gotta be careful because we're subtracting, so you can think about this as a negative 3 if you wanted to. Yes. Alright, let's go ahead and distribute in the negative 3 up top. We would have a negative 3x, then a negative 3h, and then a negative 6. Okay, so that's just if we multiplied the tops. After you subtract fractions, what do you do with the denominators? What do you do with that common denominator? If I had 3/5 minus 1/5, that would be 2/5, right? You keep the common denominator. So if we have an x plus 2 times this denominator, and again another x plus 2 times that denominator, our common denominator would be x plus 2 times x plus h plus 2. Okay, so we subtracted the tops. Okay, we combined the numerators, but we're keeping the common denominator. And let's not forget that all of that is over h. So notice how we started with 3 fractions. We had the 2 fractions up top being subtracted, and then we had the overall fraction in the limit. Now we just have 2, because we have 1 fraction up top, and then the overall limit is still a fraction. So we went from 3 fractions down to 2 fractions. We still got to go down to 1 fraction. So where do you guys want to go from there? Do you notice anything that might cancel out? Can we turn 2 fractions into 1 fraction? What do you want to do? Lots of different things. Multiply by the reciprocal. All right, so let's bring up the h, and we'll multiply by the reciprocal, which would be 1 over h. So we still have 3x plus 6 minus 3x minus 3h minus 6 all over. We now have an h in the common denominator. So there's our one fraction. Can we get cancel happy? Yeah? 3x is gone. 6 is gone. So we're just left with a negative 3h up top. Anything else can we say is gone? If this is all that we're left with up top, the h down below will cancel out with that h up top. So we have negative 3 over x plus 2 times x plus h plus 2. Let's try plugging in 0, because we did all of our cancellations. Maybe it'll work now. If the h goes to 0, okay, that h is going to disappear. So we're left with an x plus 2 times another x plus 2. So we could probably represent that as x plus 2 squared. Okay, you have two of them being multiplied together. So there's your derivative, okay, the slope at any point for the original function you started with. You can pick any x value you want. Within reason, I'd say. Notice how you can't pick negative 2. Why can't you pick negative 2? Because the bottom would be 0. Okay, so in some instances you can't pick any value, but you just got to be careful about what would make a denominator 0. Okay, so we're still using a single limit, okay, the derivative limit, but depending on the equation, you're going to have to use those properties or techniques of limits that we did in the first unit, like conjugates, fraction work, expansion, okay, that's why we had to do it first. So let's go ahead and use these derivatives now that we know what they are to help us perhaps figure out the equation of a tangent line at a specific point. If we were to draw the curve and then draw a line just touching the curve at one spot, we're going to figure out the equation of a line. What information do you need to know in order to write the equation of a line? What would be useful to identify? Yeah. A point. Yep. What else? Usually we would prefer that point to be the y-intercept because that's the b value, but you might not have that luxury of knowing that specific point. You may know some other point. What other characteristic of a line would be useful to know in order to write the equation? I heard it. Slope. Okay. You need to know a point and you need to know a slope to write the equation of any line. So let's go ahead and see what we can figure out here. We want to find the equation of the tangent line to the graph of the square root of x plus 2. Okay, that's the example we did at the very top, specifically at this location x value of 7. So in order to find the point, which equation are we going to plug in 7 to? Because right now we have two equations. We have the original equation and we have the derivative equation. It can get confusing which one to use when. Which equation would give us a point value, aka a y value? A circle on our graph, yeah. The original, right? Because isn't f of x the same thing as y? So let's go ahead and plug in 7 into the original equation. We would have the square root of 7 plus 2, which is the square root of 9, aka 3. Which equation are we going to use to figure out the slope of the line at this specific point? What represents the slope of a line at one point? I say that phrase and you think derivative, okay? So we're going to plug in 7 into the derivative equation, which we found at the top. Okay, 1 over 2 times the square root of 7 plus 2. 7 plus 2 is 9, square root of 9 is 3, 3 times 2 is 6. So it looks like our slope is 1/6. Okay. So now that we know the point and now that we know the slope, how can we combine those two pieces to finally write our equation? Do we remember point slope form from yesterday? Okay, because that's the information we know. What would it look like? Y minus 3. Okay, that's the y value, equals the slope, yep, 1/6 times x minus the x value, which is 7. Good. You can leave it like that. If you want to change it into slope-intercept form, you could, but you'd be dealing with fractions if you wanted to work with fractions. We doing okay? Let's try another one. We're going to find the equation of a tangent line to this fraction rational graph that we did at the top. Our specific location is 1. So we got to figure out what is the point value at 1 and what is the slope value at 1. If you plugged in 1 into the original to get the point, looks like we would get 1. And if you plugged in 1 into the derivative to get the slope, okay, we're going to use the derivative from the top that we found. See, 3 squared is 9, negative 3 over 9 is negative 1/3. Can we write the equation? Yep. What would it look like? Y minus 1 equals? Yep. X minus 1. You can leave it like that or convert it to slope-intercept form, whatever you feel like doing. Is it starting to sink in a little bit more today? Yesterday was a little rough. I think we do better with kind of computations and algebra work. I'm hoping it's starting to sink in. Okay? We'll stop there for today. We're going to do more with it tomorrow and the rest of this semester, to be honest.